Yeah, hello everybody. Today the topic is instruction sets of MSP430. So, for any microprocessor or microcontroller, the heart of microcontroller or microprocessor is in the instruction set. The instruction specifies so which instructions are to be acceptable from the user and which instructions are not acceptable from the user or the programmer. And here for MSP 430, there are about 27 instructions which are native instruction we call, and there are about 24 instruction which are calling it as emulated instructions. So totally 27 plus 24, I think what about 51 instructions are available for the MSD 430. And let me go through each and every instruction. First of all, move instruction. Move, for moving or for transfer, there is only one instruction that is available with MSP 430. The mnemonic for is move.w. Of course, here we have used .w. Still, it applies for byte when I use move.b. And for the um, syntax for this is move.w or b space src comma destination. So for this, source will be on left side and destination will be on the right side. It is unlike to the Edge 86 or any other general microprocessor C. Okay, so because of this, the data available at the source will move to the destination. And here, the source and destination either may be of a memory or maybe of CPU registers. So and hence there is no need of like a load, store. Okay, so these all can be done only with one mnemonic calling it as move. And for dealing with a stack, here we're having two push.w or pop.w, or w may be b for any of these instructions. So when I say push.w src, so whatever the data contained in the src will pushed onto the stack, and its stack pointer will be changed then. And while popping, so the data will be popped uh, from the stack onto the destination. However, the pop instruction in MSP 430 is the emulated. Push instruction is going to be the native, and the pop instruction is going to be the emulated. The meaning of that one is the pop instruction can be implemented with the addressing mode calling it as post increment mode, or we call it as auto increment mode, auto increment indirect register mode that is available with MSP 430. Hence, use of this instruction, we can implement this pop. Whereas for push, we require pre-decrement addressing mode, so that is not available with us. Hence, for that dedicated instruction is there, and for pop, the emulator instruction is to be available. And coming to the arithmetic and logic instruction, here again in arithmetic, you'll be having binary arithmetic and decimal arithmetic. Again in binary arithmetic, so you are observing two. One is with two operands, other one is with one operand only. So, for example, when I say add W source comma destination, so source data and destination data will be added and will be moved to the destination. But we call it as destination plus equal to SRC, meaning that DST equal to DST plus SRC. And similarly, add with a carry. So along with the source and destination, carry is also added and it will move to the destination. And one more thing is we have ADC. ADC nothing but add carry. It is not add with carry, it is only add carry. So whatever the carry generated previously, that is going to be added to the DST and it will be available in the DST. Sorry, it will be available in the DST itself. However, this is not the native and this is the emulated instruction, because so this instruction can be executed with this instruction. Means whenever this instruction occurs, so the assembler converts this instruction as this one. After that, it is going to be executed. But instead of source, the source can be taken as 0 because for this there is no source. Therefore, when source equal to 0, destination plus equal to 0 plus c, nothing but c. So when these are going to be the same. Hence, add with a carry or add carry bit is going to be the emulated version. And similarly, coming to the subtraction operation, subtraction with borrow and subtraction borrow, which are similar to that of add with carry, add carry. However, for subtraction with carry, so for actually it is not carry, it is borrow, but borrow is not having a dedicated pin or signal, but that is identified with a carry only. But here, instead of plus c, we are going to take a negate c because this is the borrow, hence we are taking it as negate c. However, subtract borrow or subtract borrow beta, that is emulated version of this subtract with borrow, just like ADC in terms of ADTC. And other than that, one more instruction is compare. In this comparison, okay, the DST minus SRC can be done, and accordingly, the flags are only affected. This is just like similar to that of the subtraction, where in subtraction the result updated in the DST, whereas in this the result is not updated in DST. However, the flags are going to be affected. The flags of SR register are going to be affected. Yeah, let me see the arithmetic instruction with one operand. These all operands almost are going to be the emulated only. So if you observe clearing nothing but what? Making some register as 0. So here we need to make a DST as 0. Therefore, this can be emulated like mode.w 0 comma DST. So instead of source, if you take 0, this becomes the clear instruction. Similarly, decrement. So whenever you use subtraction, and in subtraction, if you take a source as 1, source as 1, then nothing but destination equal to destination minus 1. So that is nothing but decrement. Similarly, decrement double means the source is to be taken as 2. Increment. So take add instruction and take a source as 1. And if you take a source as 2, it is increment double. And finally, coming to the test. Test is similar to that of compare, but here the comparison with 0. It is the comparison with the 0. Therefore, these are all emulated versions of the native instruction. So these about arithmetic binary instructions for two operands and one operand. Now we'll see decimal arithmetic. Decimal means BCD. For dealing with the BCD data and BCD display, so the BCD data is to be available and BCD data is to be computed. That's why here we're having a decimal arithmetic separately with an instruction called as a DADD, that is a decimal add with a carry. Decimal add with a carry, that is nothing but SRC plus DST plus C is to be given to DST. And one more instruction we have, that is only decimal add carry. It is just like a ADC, addition with a carry. This is the emulation of this instruction. So these are the decimal arithmetic that are available. So with these arithmetic instructions are completed, now we'll move to the logic instruction again. Again, these are with the two operands and with the one operand. With and one more difference here you can observe for MSP430 is here you are going to observe and exclusive R, and you are not going to observe the inclusive R here. You are not having the R operation here, and these logic instructions are going to be the bitwise. So bitwise ANDing, bitwise XORing, and this is going to be the test. Bit test is simply the bit ANDing only. However, the flags are going to be affected. Here, the destination is not updated. However, only the flags are going to be affected. Now, bit set to particularly set a bit, so that then we need to use of this bit select and bit clear to particularly clear a bit in a register, you can use of this bit clear. So these are logic instruction with the two operands. Now coming to logic instruction with one operand, there is only one instruction we have, that is inversion. That is also the emulated version. So how you are going to emulate? If you use a XR instruction in which the SRC is -1, when SRC is -1, all are going to be 1. Then what happens? One XR of some data, it is going to be one XR of some X. It is going to be the X bar. So in this way, inversion can be emulated of XR by taking SRC as -1. Anyhow, I will show you the table of a list of emulated instruction in terms of emulated instruction in the last slide. Now coming to the byte manipulation instructions. Byte manipulation. Here we are having two instruction for byte manipulation. One for swapping the bytes. So lower byte to the higher byte, upper byte to the lower byte. So this is generally required whenever we want to deal only upper data. Only dealing of upper byte of data is not recommended, is not useful actually. The data which is available in the lower byte only, it can be added, it can be done with any operation, but not the upper. In that time, you can just swap upper with the lower with the upper, then you can do that. And coming to the extension of sign power, extension of lower byte. So whenever you are converting from you are converting from byte to word, and that byte is going to be the signed one. Then the sign bit of that byte is to be extended when it is converted into the word. So this can be done by this extension of lower byte. That is a sign bit of the lower byte will be applied to the upper byte. So these are about byte manipulation. Now let me go to the operation on bits of status register, or we call it as status register bits manipulation instructions. So whatever the bits are available in a status register, like clear, like a carry, negate, zero, so interrupt. So these are all can be manipulated with instructions, and all these instructions are in general the emulator instruction, calling it as a clear C. So here the carry bit is to be cleared. So we can use of BIC and BIS for dealing all these: clear negate, clear jet, set source, set carry, set negate, set zero, disable interrupt, enable interrupt. So these are all you can use by using only BIC and BIS. That I will show you later how these are emulated. And finally coming to the shift and rotate instructions. So in shift and rotate, there are mainly three: logic shift, arithmetic shift, and a rotation. And you can observe easily here these three types of instruction. And again, these three are for left and the same are for right. So in left shift operation, so in logic left shift operation, what happens? So whatever the vacant bit created in the least significant bit, which is going to be inserted with a zero. And similarly for right shift of logic shift, so most significant bit is going to be vacant. So there also zero is going to be filled. Whereas coming to the arithmetic shift, these are generally useful for shifting the signed numbers, logic shift for unsigned numbers. So for arithmetic shift, and coming to the arithmetic shift left, so arithmetic shift left is same as that of logic shift, and whereas coming to the right shift, arithmetic right shift, in arithmetic right shift, to not uh, change the sign of the to not change the sign of the number, to not change the sign of the number. Here MSB is going to be replicated. Here MSB is going to be replicated. And coming to the rotation, in rotation there is no loss of the data. So whenever in the right rotate left shift, so LSB is going to be vacant. So that vacant LSB is going to be inserted by the carry bit. Similarly, in rotate right shift, vacant MSB is going to be inserted by the carry bit. So in this way, we are having totally about six operations. But for six operation here, we are having only four, because a logic shift and right shift can be operated using arithmetic shift and arithmetic right. That's why we are having only four. So first one, RLA, that is arithmetic shift left. RRA, arithmetic right shift. RLC, rotate left with the carry. RRC, rotate right with the carry. And among these, sorry, only right instructions are going to be the native instruction, and left shift operations are going to be the emulated. So how these are emulated, I will show you in the last slide. Okay, so, but right arithmetic right rotation are going to be the native instructions, and by using arithmetic shift left and arithmetic shift right, we can do a logic shift left and logic shift right. Now going to the flow control. So whenever the the execution is to be moved from one location to the another location, we can use all this flow of control instructions, that is in subroutines for dealing interrupts or branches. We can use our flow of control instructions. First of all, br nothing but branch, then call, return from interrupt, and no operation. These are all flow of control instructions. So whenever I do branch, so from actual sequence of execution, the CPU enters into a line which is available far from the actual line. So in that point, we need to add, or we need to insert address of PC to the destination. Hence, the branch instruction can be done by moving the data PC into the destination, or otherwise the DST contains the address. So that address, if you move to the PC, then the branching can be done. Hence, this is going to be the emulated instruction. And coming to the call, so call generally same as branch, but a call is about for far distances. Hence, this call is to be dedicated instead of emulated. Hence, the dedicated native instruction is to be given for call. And coming to return, so whenever you are returning from subroutine, so you need to get back your address of the CPU program. So when you get back, when you get that return address, this can be executed. Hence, this is going to be the emulated. Whereas for return interrupt, so there is a separate instruction is to be available. Hence, for RETI, native instruction is given and no operation. So no operation doesn't consume any cycle, but this is useful for making some delay, and for buffering we use of this no operation. And finally, coming to the jump instructions, the jump instructions, again it may be the unconditional jumps or conditional jump. In unconditional jump will be available jump and branch, so jumping and branching. So whenever the jump is there, it is going to jump within one plus or minus 1 kb from the current location, either to the previous location or to the next location within plus or minus 1 kb, that we call it as jump. And coming to the branch, whenever you do the branch, so it is out of this plus or minus kb, that we call it as the branching. And coming to the conditional jump instructions, so these conditional jump instructions generally operated on various flags of the status register, like JC, JNC, JN, JZ, JNZ. Nothing but when carry is there, then jump is to be done. When no carry is there, jump is to be there. When negate is there, that is a negative number is there, then jump. When zero result is there, then jump. When there is no zero, then jump. So in this way, jump on some condition is there. So which are based upon the condition of flags of the status register. Now, another set of jump instructions are based on their comparison. When the result is equal, I mean, when two numbers are equal, when not equal, when higher or same and lower. So in that case, we can use of these instructions. However, these are same as that of the earlier one. And coming to the last, so whenever we use of signed values, these above four values are for unsigned. Whenever we use of signed values, so whether one number is greater than other, whether another number is less than other, to to have that result, we'll use of this JJE and JL. So in this way, we're having a conditional jump instructions. Finally, I will show you the emulation instruction in terms of native instruction. As I told you, ADC can be implemented in terms of ADDC with a source value 0 and branch. For branch, D is to be loaded into the PC, and for clear, 0 is to be loaded. And for clear carry, clear negate, clear 0, so wherever the carry bit is there, so wherever the carry bit is there, so there we are going to insert 1. Accordingly, it may call it, it may get the result as 1 or 4 or 2 or 8. So in that way, by using bit clear, so we can clear the respective carry bit or negate bit or the 0 bit. So in this way, we are going to clear respective bit by using BIC. And these are all, I discussed, and this gives an overall picture of emulated instruction in terms of the native instructions. For no operation, if you observe specifically, no operation is nothing but storing one register content into the same register content. So nothing but there is no operation at all. For this, there is no consumption of the cycle. And for pop operation, you are using here auto increment operation or post increment operation. So in this way, so these are the native instructions, these are the emulated instructions. Yeah, thank you one and all.